Hello everyone. In this lecture, I am covering the number system and particularly the base conversion between different way of representing numbers. So, a number is represented with its positional notation. For example, a decimal number is represented as 987.34 with a subscript 10. This subscript 10 means it is a decimal number, and there are in this number system there are 10 unique digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And another example is given in a binary number system. The number is 101.01 with a subscript 2. This 2 indicates it is a binary number system which has only two unique digits 0 and 1. And the point is the radix point or the base point, and the portion which comes in front of the radix point, it is the integer part of the number, and the digits that comes after the radix point, that is the fractional part of the number. Now we already know r is the radix of the base of the number and n is the number of integer digits to the left of the radix point in the integer part, and m is the number of fractional digits, and a with a subscript n minus 1 is the most significant digit and a minus m is the least significant digit. Now, after representing the number, we have to know what value it represents. For decimal number, we know the value, but for binary number, how much it is, what value it is, that can be determined by a polynomial notation or series expansion. In this polynomial notation, any number of any base is expanded like this. This is the digit, most significant digit, times r is the base to the power n minus 1, the location or the position of that digit. And you keep on, this is the value of that digit in that particular location. And so if you like that, if you sum up all the digits, that means the value of that digit in that location, you get the value of that number. Like 251.41 with a subscript 10 is a decimal number, so it can be expanded like 2 times 10 square because this 2 is in the second position, plus 5 into 10 to the power 1 plus 1 into 10 to the power 0 plus 4 into 10 to the power minus 1 plus 1 into 10 to the power minus 2. And you get this 251.41. The same thing we can do for the binary number. So what value it represents? So it will be 1 times 2 square, that is 4, plus 1 times 2 to the power 0, that is 1. So integer part is 5, and in the fraction part it is 1 times 2 to the power minus 2. That means 1 divided by 4, which is 0.25. So this number 101.01 with a subscript 2 represents 5.25 in decimal. So this way of representing the number in polynomial notation and evaluating its value, transfer the number from that base to its value in decimal notation, decimal representation. So binary, octal, decimal and hexadecimal, these are the popular number system. In binary number system, it is also called base 2. It has two unique digits 0 and 1. In octal number system or base 8 has 8 unique digits 0, 1, 2, 3, 4, 5, 6, 7. Decimal number system or base 10 has 10 unique digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And hexadecimal number system or base 16 has 16 unique digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and after that it uses letters A, B, C, D, E, and F. And A has a value of 10, B has a value of 11, C 12, D 13, E 14, and F 15. So from 0 to 15, total 16 unique digits that can be used in hexadecimal number system. Now, because there are so many number system, there needs to be a conversion method from one number system to another number system. Now, we have seen this polynomial representation of a number. For any number of any base, it is represented in this polynomial series, the digit and the base, what it is using, and the digits position. And now, if this equation is evaluated, it gives us a decimal number. So that is the equivalent of that number in decimal system. Now we need to convert a number of any base A to any other base B, not necessarily a decimal number. So we can first convert the base A to decimal representation and then from decimal representation to base B. And let's see how it is done. So base 1, we have seen it before, how a number is evaluated in a decimal number system, and then we will see the step 2 from decimal to the other number system. Now here it is giving an example of a binary number 1101 0.1, and it is coming out to be 26.5 in decimal after the polynomial expansion. And this number 6 to 7 in octal is coming out to be 407 in decimal, and 6b in hexadecimal is coming out to be 107 in decimal. Now after decimal, suppose we want to convert a binary binary to hexa. So intermediate step was to convert the number in decimal first. So from decimal, how to convert the number in binary, we are going to see. So let's see. Now decimal numbers have two parts. One is the integer part, another is the fraction part. So it can be a decimal real number, integer, then the radix point, decimal point, then the fraction part. Now the rule is different for converting the integer part from the fraction part. So if we have to convert the decimal integer to binary, then we will divide the decimal number by 2 and take its remainder, and the process is repeated until it produces the quotient of 0. The binary number is obtained by taking the remainder part from each division from bottom to the top. So we must remember that we will be collecting the remainder from bottom to the top, and we are going to divide the number until the quotient becomes 0. And this is called the division method. And for the multiplication, for the fraction part, from decimal fraction to binary fraction, we will be multiply the fractional part of the decimal number by 2. Record the integer and fraction parts of the product separately. Repeat the process until the fraction part becomes 0. Sometimes the fraction part doesn't become 0 for a long time, so we take a approximation. We just do 3-4 steps and then stop it. The binary number is obtained by taking the integer part from each multiplication from top to bottom. Let's see with an example, it will be clear. So there are two methods. One is converting the integer to binary, and another is converting the fraction. to binary. And this is just a binary conversion. We can convert it to octal. So if we want to convert the decimal number to octal, so here we will be replacing 2 by 8, and here also we will be replacing 2 by 8. And if we want to convert decimal to hexadecimal, then we will divide the number by 16 repeatedly. And for fraction part, we will multiply the number by 16. Let's see, decimal integer to binary conversion. So 23 is an integer number, and we are looking for binary conversion. So we are dividing 23 by 2. So the quotient is becoming 11 and the remainder 1. Again you divide by 2, quotient is 5, remainder 1. Again 5 divided by 2 is quotient 2, remainder 1. Again then 1 and 0, and here 0 and 1. When the quotient is becoming 0, you are stopping, and now you are collecting the remainder. This becomes the most significant bit, and this becomes the least significant bit. So 2310 is equal to 10111 in binary. As I said, it will be the same thing for decimal to octal and hexadecimal conversion, only instead of 2 we'll be using this particular base 8 and 16. So if we have to convert 315 in decimal to octal, we'll be dividing 315 by 8 repeatedly, and then the number is becoming 473 in octal. Similarly, for hexadecimal conversion, we are dividing the decimal number by 16 repeatedly, and we are getting the result 13B in hexadecimal number. So this is about the integer part. Now for the fraction part, it is the multiplication method. Suppose we have to convert 0.479 in decimal to binary. So we are multiplying 0.479 by 2. We are getting the result 0.9580. Now 0.9580 is getting multiplied by 2, and it is giving 1.9160. Then 0.9160 multiplied by 2, the result is 1.8320. And 0.8320 multiplied by 2, 1.6640. And when we are going to report the fraction, this is my most significant digit, and here it is the least significant. So we are reporting it from top to bottom, only the whole part. Okay, so the number is becoming 0, 1, 1, 1, and we could keep on going, no? Fraction has not become 0, but it takes a long time for the fraction to be 0 for some numbers. So after few steps, we stop it, and the result is this approximate number. Similarly, for decimal fraction to octal conversion, we will repeatedly multiply the fraction part of the decimal with 8s here, and we'll be reporting it as 3651 in octal. Similarly, for hexadecimal number 0.47910, we are only taking the fraction part and multiplying it by 16. Every time we are multiplying the fraction with 16, and we are reporting the result from top to bottom 7A 9F. Okay, now I'll be solving some problems by hand also, and let's do that. We have to convert a decimal number to a binary number. The example one, first number is 100, which is an integer in decimal. So we'll be repeatedly divide this number by 2. We'll be using division method. Now divide 50. So ultimately we got the quotient 0. So now we have to report from bottom to top. So the number will be, so that is the result. 100 in decimal is equivalent to 1100,100. You can also verify it with its positional notation, polynomial expansion. So this value, this one is 2 to the power 6 is 64. 64 plus 32 is 96. 96 plus 4 is 100. Let's do another example. Here it is 127 integer, decimal number and integer. So let's divide it. We are dividing 127 by 2 repeatedly in example 2. Okay, so ultimately the quotient is 0. So the result is, let's verify this number with its positional value. 64 plus 32 is 96. 96 plus 16 is 112. 112 plus 8 is 120. 120 plus 7 is 127. So this is right. Now we'll be converting decimal fraction to binary fraction by the multiplication method. First example is 0.57 in decimal. So we'll be multiplying it by 2 and the result is 1.14. Next time we will be multiplying only the fraction 0.14 by 2 and we are getting 0.28. Now 0.28 multiplied by 2 is 0.56. Now 0.56 multiplied by 2 is 1 point. So we can keep going because the fraction part is not 0, but we can stop here and we'll report the approximate representation. That will be, and this time we'll be reporting only the whole part from top to bottom. Okay, so let's verify it. The position after the binary point is 2 to the power minus 1. So this one is zero point 0.5. We got zero point 0.5 from here. So this one gives 0.25. We don't need that. This one gives 0.125. That is also not needed. Next is 0.0625 because we have gone for approximation. So this is, we are reporting up to this. Let's solve the second example. 0.12 in decimal, how much is in binary? So 0.12 multiplied by 2 is 0.24. Next time we'll be multiplying 0.24 by 2 and we are getting 0.484. Next time 0.48, we are getting 0.96. Then we'll be multiplying 0.96 by 2 and here we'll be getting 0.96 multiplied by 2 is 1.92. So we'll be stopping here and report the approximate representation, and that will be 0.0001. And you can verify it because this position in binary is 0.5, this position is 0.25, this position 0.125, and this position is 0.0625, and so there will be more ones after this, but we are reporting up to this. So hope this is clear to you how to convert the decimal integer part and the fraction part separately, and then you can add them together, represent them together. So next time I will be covering decimal to hexadecimal conversion and also binary to hexadecimal conversion direct way, binary to octal conversion in direct way.